Hello everyone. So this is the second lecture on this Titanic machine learning project, which we're using as a case study for project management, machine learning, and developing for production. So here we're taking the data science skills that we've learned throughout the course and not only applying them to a particular challenge, but additionally learning what working through a challenge might look like in a professional environment. So, the previous lecture closed with an introduction to Git, which is a version control software we use for monitoring changes to code and helping us keep track of how a project evolves, especially as multiple contributors collaborate on a project, which may involve many lines of code and which, like, we can't necessarily feasibly just remember the state of at any given time. So where I left off, we had created a Titanic.py file which contained a few lines of code from our IPython notebook that clean up the training data. And we had checked that into Git. So I want to transition here from talking about the version control software and that aspect of project management and talk about how we organize projects in terms of how we write code and how we develop code for a kind of general use where we can easily deploy it in one or more applications. And key to this is treating our code as modular, meaning breaking it into pieces that accomplish simple, logically kind of unitary tasks, and then combining those modules into larger applications. And modularity occurs across different levels of hierarchy. The lowest level is simply putting our code into functions. So currently, this script imports pandas, it loads in the training data, and it modifies it. I'm just going to reload this real fast. Here we go. So we could, if we add here a print statement and save this, we could run this script as a Python script using the Python interpreter, and it would run these lines of code and it would print out train.head at the end. One thing I will need to do is move the data into this folder. So now our training and test data is in this folder as well. And if I run the script, I used X here. And here, even though I didn't actually declare a variable x in the first place. Remember, I didn't split up training into x and y in the last lecture, so I'm just using train here, no variable x. So what we did is we tried to run Titanic.py, we discovered there was a bug, and then we fixed the bug. Well, if we fixed the bug, we should check that debugging change into Git. So we'll do git add Titanic.py, and we'll commit with the message fixed name error. So now our Git log has two commits. That first commit we made in the first lecture, and this little bit of debugging we just did. So now, if I run this script, it shows me the head of the train data frame. And this is fine, but we'll not only want to do this for the training data, but also the test data. And we might want to read in different files from different places in our operating system. So it could be good to start putting these things into functions that let them respond to how we want to run this script, and where we can apply these operations to different inputs. So the first thing I'll do is define clean data, which takes in a data frame. I don't care if it's the test data frame or the training data frame. So we'll indent all of this so that it's part of the clean data function. And all through here where I use the training data frame, I'm going to change that to df. And now I could do something like train equals clean data train. Print train dot head. And this will give me the exact same output as before. None type object. Yes, I need to return this data frame. So this returns the exact same data frame as before. But now we could easily apply this to the test data frame as well. It's not limited to the training data frame because I don't hard code that these things should happen to the training data frame. I say this function accepts some data frame and then does these transformations to it. I'm going to additionally make some stylistic changes that are not they're stylistic changes. You don't necessarily need to do these things. They just address some pet peeves of mine. Okay, Now, we can go on making more changes to increase the portability of this code and its modularity. But for now, I'm going to just leave this as is, and we'll come back to that in the future. But one thing I do want to address is when we run Python scripts, it is good style to say, have a clause at the bottom, if name equals main, and then we put code in this if statement that defines what it means to run this Python file as a script. And this relates to the modularity of Python as a language. So often we use Python files as modules. For example, here I import pandas, and that's going to import all kinds of Python files on my computer that define how data frames work, how pandas series work, how does pandas read CSV work, all these different elements of pandas. And when I do that, I really just want access to any class and function definitions. I'm not trying to accomplish some task or take some action when I import pandas. I just want the functions and classes. So, Python includes a syntax for discriminating between when we want to just import a Python module to use its functions and classes versus when we want to run a Python file as a script. So if we import a Python file as a module, only this part of the file will get run. When we run a Python file as a script, the Python interpreter will additionally run this if name equals main clause. And so we put any code that defines how this Python file should run as a script, as a application, in this if statement. So, for example, if I start an IPython interpreter here, and I say from Titanic import clean data, I now have this access to this clean data function. It's a part of my environment in IPython now, but nothing else happened. It did not run this section at the bottom of the script, because this section only gets run if I run this file as a script. For example, if I exit IPython and run the Python file as a script. Cannot use label indexing with a null key. I think this will fix it. Yep. So here, the Python interpreter said, oh, I'm running this Titanic.py file. So I'm running this as a script, which means I will execute this piece at the bottom here, in addition to running these imports and function definitions. So now we've made a few more changes. We check in with Git and it tells us, we modified Titanic.py. So we'll go ahead and make another commit. Modularize code, add main. So we're slowly building up our project, and we're documenting all of the changes we make along the way in our Git version control. Now, just before I turn back to the machine learning task, I want to emphasize how useful Git is. So say I remove this line, and I think this is a good thing to do, so I commit the change. This is a super great idea. So now in my commit history, I have this commit where I committed my super great idea of deleting that line, but that line was useful. How do I get it back? Or how do I examine what changed? Well, I can look at differences in Git. So the difference between the current state of things and the state of things one commit ago. So one commit prior, I apologize for the noise, that's my cat shredding my furniture. So one commit ago, I used to have this line, and in the current version, in the current commit, I have deleted it. So Git shows me that I've deleted this line, minus this appears in red. If I decide this is not such a great idea, I can revert this change. So I'll do git revert ed7cca, and I'll include a message here saying not such a great idea after all. But I used this command incorrectly. Git revert options. So I need to put maybe the commit hash after the message? No. Let me get rid of this message. So now we have a new commit, revert, super great idea, this reverts commit, blah, blah, blah. So we've changed back from the deletion. And if I reload this file from disk, really tiny down here, you probably can't read it, but it says file titanic.py changed on disk, reread from disk. Yes. And that line that we deleted before, we've now recovered using Git. And Git is full of like other helpful things. We can search for particular expressions. So if I'm trying to find, for instance, where I do group bys or something. So this shows me I do a group by in the Titanic.py file, and here's the line of code where I do it. So this can be really useful for searching through projects, trying to find particular elements of the code. And in general, Git's a very useful tool for just keeping track and working on code. Okay, so that was a whole lot of kind of like engineering and development stuff. Let's get back to the data science so that we actually have somewhat more to work with. Okay, so I'm actually going to change our notebook to reflect our Python file that we're working on. A lot of this exploratory stuff we don't need anymore. So now we've got our cleaned training data. So now it's time to actually start thinking about how we're going to use this data to predict who survived, who didn't. So let's start digging more deeply into the data and particularly studying the relationship between the different variables we have access to and whether or not they survived. So, for instance, for P class in train P class unique, let's see what do I want to do here? Let's actually, let's make two plots, one for the group of people who survived, one for the group of people who did not. So for serve in train survived unique, and we know this is just 0, 1. We'll do train train survived equals serve p class dot hist. Let's just try this. No, that doesn't look very good. So here I'm going to pick out the survivor group, P class, and the group that did not survive. Sorry, this is backwards. So I have the people that did not survive, followed by the people who did. And we're just going to make two different histograms. So, let's see here. I'm gonna put here title, perished, title, survived. There we go. And these are overlapping in a pretty unpleasant way. There we go. So we can see these two plots look quite different. And in particular, among the survivors, it was pretty evenly distributed among the different classes. Survivors were equally likely to be pulled from all three classes, 1, 2, and 3. But among those who perished, it was very likely that you were lower class. So, for instance, if we calculate the survival rate for each class, train P class, or group by P class, survived mean. So 63% of the first class passengers survived, 48% of the second class passengers survived, and less than 25% of the third class passengers survived. So this is obviously going to be a pretty important predictor. We can easily distinguish between survivors and non-survivors based on their distribution across class. So this is going to be a valuable variable. Let's similarly look at age. So we might expect that the very young were more likely to survive. So we'll just change this P class to age. This is not working right. Oh no! um, my clean data function didn't work correctly. Aha. So here we were setting the values of people's ages. We were intending only to do it where the data was missing, but in fact we did it to everything in a given class. So we need to add an additional logical statement here where we say df age is null. And here's the distributions we wanted to see. So now I have the correct ages. Let's not forget, we are simultaneously putting this in a Python file. So we're going to go ahead and make the same change here. Check that change into Git. So we just fixed the age assignment bug. Great. So, indeed, if we look at the survivors and those who perished, the distribution of ages in both groups looks pretty similar. However, notably, among survivors, there's a big spike in ages close to infancy. So infants were much more likely to survive. So age will also be a useful variable for discriminating whether or not someone survived. It's not totally clear that necessarily their exact age is all that helpful, but certainly at least knowing whether or not they were an infant would be helpful. One thing we could do would be to create a variable called infant, which would simply be a threshold of age, say below the age of, let's say, 10. We don't necessarily want to do this, but we can put this down as an idea to try later. This may be a useful data transformation to apply to our training set to make this spike stand out to our estimator. The age may not be so important. You know, whether someone was 20 or 50 doesn't seem to really have that much impact necessarily. The distribution above 10 years of age for the survivor group and the non-survivor group looks fairly similar. But this spike is notable. And so there appears to be kind of like two things going on. If you were older than 10, it didn't really seem to have too much impact on whether or not you maybe lived or not. If you were under 10, though, that appears to be a big advantage. So we might want to treat 20s and 30s and 40s and 50-year-olds all more or less the same, but treat young children differently. So we can continue exploring the data in this way, looking whether sex matters, number of siblings and parents. But I want to first make a slight segue, because as we further explore the data, we're going to encounter more choices like this one. How do we transform our data to make it most available to our model for making good predictions? And before we can attack that in earnest for the entire data set, we need to discuss what to do with things like name, sex, which is male or female, ticket, and embarked. So notably, these things are all string data. They are categorical. They are not numeric. We could make them numeric. For instance, we could re-encode the embarked column to be 0, 1, and 2 instead of S, C, and Q. But these numeric values don't necessarily have meaning. For instance, S, if S was 0 and C was 1 and Q was 2, this would suggest that S is somehow more different from Q than C, because 2 is further away from 0 than 1. And our estimator will interpret the values in that way. We can instead encode these values, S, C, and Q, in a slightly different way. In any case, we do need to convert all the values to numbers, because scikit-learn estimators expect a feature matrix as input, and a feature matrix may only have numerical values. So some things will be very simple. So for instance, sex, we will replace male with 0, female with 1. So this is really just like a binary flag as to whether or not someone is female. Let's think about what to do with this ticket information. So there's tons of different ticket codes, it appears. How many are there? 681. There's 891 rows of data. So we have 681 ticket codes for 891 rows. So these ticket codes are they're virtually unique for every single passenger. They may contain some kind of useful information in them, but without knowing what kind of patterns might be in the ticket information in the first place, without knowing what the ticket codes signify, it's very unlikely that we'll be able to extract any useful information from this ticket. So we will just remove that data. let's consider embarked next. So I mentioned we don't want to encode this as 0, 1, 2 because 2 being further from 0 doesn't actually signify anything in the case of these different embarkment codes. Instead, what we would want to do is called one-hot encoding. So the idea here is that we will, instead of having one column for embarked, we will have 3 columns. One for embarked S, embarked C, and embarked Q. And of these 3 columns, in each row, one of these columns will have a 1, corresponding with the original value in that row. So this is where the term one-hot comes from. There is one active column for each row for our one-hot encoded variable. So we could do this manually. So now we have 3 columns, embarked S, embarked C, embarked Q, where we have S values for embarked S is 1, where we have C, embarked C is 1, and all the others are always 0. So this is called one-hot encoding. It is a very common technique for dealing with categorical data, and many other techniques for dealing with categorical data are related to one-hot encoding. I'm not going to get too much into the technical details of how to optimize one-hot encoding or the full mathematical motivation for one-hot encoding. But again, the idea or intuition generally is that if we encoded these as 0, 1, 2, where 2 was Q, 1 was C, 0 was S, S would be further away from Q than it is from C, which is not really meaningful. I don't know the relationships between S, Q, and C, and it's probably not meaningful to say that S is further away from Q than C. And furthermore, it's definitely not meaningful to say that S is twice as far from Q as it is from C. So all of these kind of statements, that S is twice as far away from Q as it is from C, are implicit in an encoding of this variable in which we assign S0, C1, and Q2. This way, every data point is equidistant from its neighbors. You can see there's no ordering here, and all these columns are in some sense kind of exchangeable. So now we've taken care of the embarked column, so we'll go ahead and drop that as well. Which leaves us just with this name column left. Now, there could be useful information in here. For instance, let's just have a look at some of the names. So there are some masters in here. There is a Don. That's a special Spanish title of lordship, I believe. Miss versus Mrs. is maybe significant. Hard to say. So, a reverend? Being a reverend versus just like a mister is maybe possibly, or being a master versus a mister maybe will impact your likelihood of survival. Because these could correspond with different professions, different social positions that would impact who was seen as important to save and who was not. So there could be important information in the name. We could do things like try to extract these titles. So train name. So titles tend to come, they're always showing the last name first, then a comma, then the title. So if we split on commas and then extract the part after the comma, and then again split on periods and extract the piece before the period, we get out these titles. So you have Mr., Mrs., Miss, Master, Don, Reverend, Doctor, Mademoiselle, Miss, Major, Lady, Sir. I believe this is another French appellation. The Countess. I bet you she survived. And Jonkheer. That's a strange one. So, this is a term of nobility in the Netherlands. So I bet you this man probably also survived. So these titles could be useful. You could additionally try and extract last names, see if there are multiple passengers with the same last name. That could possibly have an impact. In this first pass, we're just going to try and do something simple. So I'm going to leave this information on the table for now. I won't incorporate this into our model just yet, but we will again mark this as an idea to try later on. But for now, all we're going to do is just drop the name information. So now we have a feature matrix containing only numerical values. So finally, we are actually ready to begin training a model. I'm going to leave that to the next lecture. For now, I'm going to update our Python script with the new things we discovered. So we have our clean data function. We'll now augment it with a few things that we decided were we had a few drop statements where we decided things were not particularly useful. For instance, we're not going to use ticket. We're also going to one-hot encode our embarkation. And we also decided for now we're going to drop name as well. But we came up with a couple ideas that we maybe want to try in the future. So we'll add these as functions that we don't necessarily use when we run our Python script to train our model and make predictions. So this is a very long line of code, which is less than ideal. So I'm going to break that up. So we will call this split names. Or, yeah. So we're not obligated to use these things in our script, but they are now, part of the Python file. And if we decide to use them in the future, they're there for us already. So we'll commit these changes with, what should our note be? So we'll call this pre-process data. We forgot to fix up the sex column here, so I skipped over that one. Let's make sure that makes it into the file. Great. And when we run our script at this point, oh, and I forgot to drop embarked. Haha. So when we run our script at this point, we get back our feature matrix, which only has numbers. I'm also going to drop passenger ID. I should have done that a long time ago. That clearly does not contain any useful or meaningful information. So now we're getting to the point where we have a feature matrix. We've still got our target label column in there, by the way, but we have a feature matrix that contains only numbers and seems nice and cleaned up. So I'm going to commit these final changes for this lecture. I'll just give this a very generic name, small fixes. And in the next lecture, we will start actually modeling, see what kind of results we get, and then think of what kinds of improvements we could do to further extend the efficacy or accuracy of our models.